So up until now, the integration that we've done, we've been able to do using a set of very narrow integration rules. For example, reverse power rule, or your rules for integrating certain trigonometric functions. And for differentiation, we were able to proceed with just rules alone. Given a function, here is the proper procedure for differentiating it, and as long as you can identify it, you'll never go wrong. Well, the good news or the bad news is that that is not the case for integrals. I always like to say that we get differentiation rules, but integration techniques, which means you might have to try more than one integration technique before you actually evaluate the integral properly. The first of many techniques that you're going to learn is called U substitution. But before we get to the integration and all that, I want to go back to differentiation for a moment because you'd be surprised how far you can get by just remembering that integrating means undifferentiating. So we're going to take a look at each of these four functions here and simply take the derivative. So let's zoom in a little bit. Okay. So to differentiate function f here, we need our chain rule, right? We've got a power function at the highest level here, right? We've got something squared. So let's just say f prime will equal 2 times the quantity x cubed plus 2. And then in a different color, I'm going to tack on our chain rule. All right, so the derivative of the inside function here is 3x squared. Easy enough, right? All right, let's move on to number 2. All right, for number 2, again, composite function, so we're going to need our chain rule. We will differentiate the outer function first and say that g prime is, well, the derivative of sine anything is cosine of that anything. And then inside we have this x squared, which has its own derivative, which is 2x. All right, now for the third. All right, here, h prime, well, at the highest level, we've got an exponential, and I always like to think, well, the derivative of any exponential is itself, and then chain rule, right? So chain rule means chaining on this little inner function's derivative up here, so that will be times, let's see, that'll be 2t minus 3, and we'll just put that in parentheses so that we're unambiguous. And last but not least, we have function k. So k prime, the derivative of natural log anything is 1 over that anything. And then we must do chain rule with the inner function. And when we do that, we will get times 6x squared. Now, yes, many of these can be cleaned up and simplified, but for now, I'm going to leave it. Right? And so basically what you end up with when you differentiate using chain rule is an expression that uses multiplication, right? We chain on using multiplication. And now I want you to think back to what I've been saying for several lessons now, which is that there is no product rule for integrals. If you have the integral of a product, it does not work the same way as it did with differentiation, where we say, oh, that's okay, we just need to use product rule. That is not the case, right? Instead, what we do when we see the integral of a product, such as these integrals right here, we hope that the reason we are seeing a product in the integrand is because it came from chain rule. So that's our first attempt. When we see the integral of a product, we say, could this product have been a result of chain rule? And then we try to go from there. All right, so I want to bring your attention to number 1 here at the bottom, and hopefully this looks familiar. This number 1 corresponds with the previous number 1. I think we can just see it. All right. And So we already know the answer to this integral at the bottom, right? This integral right here should just integrate to our original expression for f up top, all right? Because this integrand is this derivative up here. However, we want to dissect this a little bit. So let's take a look at what actually happened when we did chain rule. All right. So if we come back up here, we remember that there were really two layers to this problem, right? There was an outer function and an inner function. That outer function was the act of squaring something, right? In fact, what was being squared? Right? This entire quantity inside the parentheses here. We were squaring x cubed plus 2, right? And then we had to take the derivative of that thing inside. We had to take the derivative of x cubed plus 2 to complete the chain rule. All right, so for now, I'm just going to say that x cubed plus 2 is our little inside function, okay? And I'm going to give that little inside function a name. I'm going to call it u. So in this case, u is equal to x cubed plus 2. Great. All right, so if we were going to sort of rewrite expression f at this point, I'm just going to do this on the bottom here. Now notice, I'm rewriting f, not f prime. All right, so function f, we could technically say, is equal to u squared, right? Because u is x cubed plus 2, and f is x cubed plus 2 squared. So great. Let's now actually go ahead and get f prime from here. So in this case, f prime is actually, right, 2u, right, if we use the power rule on function u, but we can't stop there because u is actually a function of x and has its own derivative with respect to x. So it's not sufficient for us to just say that f prime is 2u. We have to remember to do chain rule and tack on a du dx, right? It's an application of implicit, really, in this case. Because if you think about it, finding f prime means finding the derivative of f with respect to x. And if we just do 2u, that was not the derivative with respect to x, that was with respect to u. So we need that little implicit bit, right, which really is fundamentally chain rule. Okay, so now let's take a look at this expression that we have right here for f prime and see how that's basically what we have already, right? So f prime is 2u times du dx. Well, all right, what we're going to do is compare that with our expression for f prime up here, okay? Well, I can see where the 2 comes from. I can see my u there, right? Remember, u is x cubed plus 2, and then, du dx, 3x squared. Let's actually now go back to expression u and take the derivative with respect to x. In other words, du dx, right? And if we, and again, just looking from right here, all right, if we take the derivative of that little function u with respect to x, we get 3x squared. So now let's go back to the bottom here to our integral and see how the expression that we have right here for f prime is actually exactly what we're looking at in our integrand down here. Okay, so the 2, we see the 2 there pretty clearly. All right, this x cubed plus 2, up above, we had called that u. And then the 3x squared was actually the derivative of u with respect to x. So we called it du dx. All right, and so then let's just clean this up a little bit. I'm just going to rewrite it. I'm actually going to rewrite the whole thing in blue. All right, so the 3x squared, I'm not going to call that 3x squared. I'm going to call that du dx. The 2, well, you're a 2. Congratulations. X cubed plus 2, I'm not going to call you x cubed plus 2. We're calling you u. And then we've still got a dx there, right? But that accounts for everybody. And now let's clean this up a little bit. All right, so I'll have the integral, and then notice what happens. Cancel, cancel, and you just have the integral of 2u du, which is a very simple integral that we could do probably very easily right now using our integration rules, right? This would integrate to, well, the 2 is just a scalar multiple. He'll come out front, and then the antiderivative of u with respect to u will equal u squared over 2, and then of course plus c. So now I'm gonna cheat and sort of swing my final answer up here, right? The 2's cancel, and your final answer is u squared plus c. But, of course, our original problem was not given to us in terms of u, it was given in terms of x's, so that's when we just back substitute, right? We can go back up and remember that our original definition of u, right here, was x cubed plus 2. So, we'll just say that we have x cubed plus 2 squared plus c. Which, if we go back up top, wasn't that what we had originally differentiated? X cubed plus 2 squared? Yeah, there was no plus c there, but I guess in this case for number 1, c is just 0. No big deal. All right, so all of this to say that when we do use substitution, we are actually looking to acknowledge the presence of chain rule. All right, so let's go down to the bottom here and fill that in for the purpose of u substitution. The purpose of u substitution is to undo an application of chain rule. Whoops. To undo an application of chain rule. So typically what you will be looking for is a pattern of some function and then its own little derivative hanging around so that you can say, oh yeah, this probably just came from chain rule. So let's try this in numbers 2 and 3. But before we do that, there's actually an error in number 2. It should not be 2x sine of x squared dx. It should be 2x cosine of x squared, right? Because if we look back at our original, function, all right, in number 2, the derivative was cosine x squared times 2x. So notice, in the final derivative of function g, I see a function and its derivative. And so that's really going to help you figure out what should I call u when performing a u substitution, right? Simply ask the question, whose derivative do I see? In this case, you see the derivative of x squared. So x squared is your u, and 2x, it will be your du dx. So let's come back down to the integral and put that into practice. Okay, and remember, that's 2x cosine x squared dx. So in this integral, I do see a function and its derivative, right? The derivative that I see is 2x, and it is the derivative of x squared. That tells me to make u kind of like my parent function, right? So u is x squared, and then I'm going to get du dx. And the thing to remember is that you obtain du dx not from the integral, not from what you think it should be. You obtain that from right here. Look at your function u. U is x squared. What is the derivative of x squared? 2x. Great. Now let's start to rewrite this integral using u's instead of x's. All right, really what we're doing with the u substitution is simplifying the problem into something that we know how to integrate already. Okay, so I like to use this sort of bookkeeping method where I just try to sort of cross off things as I write them and just make sure that everybody's accounted for by the time I'm done writing my new integral. So here's our integral. Yep, I will even cross that off and say, great, you're accounted for. All right, instead of writing 2x, oh, well, 2x, that's just du dx. So I will write du dx. All right, and that takes care of my 2x. Well, cosine is just going to be cosine. And then, oh, not cosine of x squared, I can say cosine of u. Yep, that's a u. Okay, and then I still have to write the dx. I know we don't want it to be there, but everything still needs to be equivalent. You can't just, decide you're not going to write something. But notice, everything's, working out because the dx's cancel. And that's your hope, that if you do this correctly, all of your x's will cancel out at some point, and you will be left with an integral that just uses u's. So let's rewrite this. Oh, and we've written the dx. Okay, so the integral, I'm going to say cosine u, that's a better u, times du. And now we totally know how to integrate that, right? What's the antiderivative of cosine u? Well, that would be sine of u plus c. And then all that's left to do is back substitute, right, based on our definition of u, and say that, well, sine of u, really we meant to say sine of x squared plus c. Done and done. Okay? So now, if we come to number 3, we're just going to ask ourselves the same question. Do we see the pattern of some function and its derivative hanging around, right? And the answer, of course, is yes. This looks like the derivative of this guy up here. So that tells us how to define our parent function, all right, our u. So in this case, u is t squared minus 3t. And then again, just based on this definition right here, not looking anywhere else, let's go get du dt, just because we're using t's here. All right, so the derivative of t squared minus 3t is 2t minus 3. And then hopefully that's enough to get us going. We'll see what we need to do going forward here. All right, I'll do this one in red so that we don't get confused with the problem above. All right, so let's rewrite our integral. Now, instead of writing 2t minus 3, I can write du dt. Done. Now that e is just e. We have nothing to replace that with, so we're just going to leave it as e. But instead of writing e to the 2t, or I'm sorry, e to the t squared minus 3t, we can say e to the u. And that takes care of the e, that takes care of the exponent. We still need to write the dt, it looks like. So let's put the dt in there, and then everybody's accounted for. And then, oh look, the dt's cancel. And we are left with the antiderivative of e to the u du, which, I mean, it doesn't get easier than this, right? The antiderivative of e to the u is e to the u plus c, and then last but not least, we will back substitute and replace u with its equivalent expression in terms of t, which would be e to the t squared minus 3t, that's a minus sign there, all right, plus c, which, if we look back at our previous number 3, should be exactly what we started with. All right, so I'm going to leave number 4 for you to try on your own and confirm that you get back to the original function k in the previous number 4, all right? But otherwise, I would like to move on to some little nitty-gritty things that can and will happen when you're performing a u substitution on the next page. Okay, so for now, let's just practice finding the function derivative pattern when we don't know what the answer is already supposed to be. Okay, so in this first example, 4x cubed times secant squared of x to the 4th dx. All right, well, the question is, Do we see a function and its derivative hanging around somewhere? And the answer, hopefully, is yes, right? I notice that this x to the fourth is here, and the derivative of x to the fourth is 4x cubed. So that tells me that this is my u, and this is here is my du dx. So let's start to rewrite based on those definitions. So here we'll say that we know that u should be x to the fourth. And now if we calculate du dx from that definition, du dx is simply 4x cubed. So now let's start to rewrite our integral and cross off things as we scoop them up, right? Of course, all the while replacing x's with u's. All right, so here's my integral. Let's cross it off. All right, 4x cubed. I don't have to write 4x cubed. I can just write du dx, and then you're taken care of. All right, secant squared. I don't have anything for that. I just got to write it. Secant squared. All right, but instead of writing secant squared of x to the fourth, I can write secant squared of u. And that takes care of this. And then I need to write a dx still. But that leaves everybody accounted for. And then, of course, this will clean up nicely, right? Because just like we hope, our dx's cancel, one on bottom, one on top, and I can now write the integral of secant squared of u du. And we know what the antiderivative of secant squared is, right? That would be tangent of u plus c. And so now the last step is just to back substitute so that we give the answer in terms of x, right, that was used in the original expression. So instead of tangent of u, right, we will have the tangent of x to the fourth plus c. And if you go ahead and differentiate this expression in black, you will get the expression that was originally in your integrand, provided that you remember your chain rule. All right, example 2. Okay, here, all right, again, we're looking for that function derivative pattern. All right, so do I see a function and its derivative? Yeah, right? If I start with x cubed rather, and I take its derivative, I get 3x squared. All right, so my function should be my x cubed, right? Furthermore, we'll throw the plus 1 in there too. There's no reason not to throw in the constant. It will just go to 0 when we differentiate it. So let's say that u is x cubed plus 1, right? No reason not to throw the plus 1 in there. It doesn't change anything. All right, and again, don't worry about the square root. You don't have to account for everything in your definition of u. Just really think to yourself, whose derivative do I see? Okay, so now from here, again, don't look back at your integrand now that we have u. Just look here to calculate du dx, which would be 3x squared. All right, let's start rewriting up here. Come on, pen, you can do it. There we go. Alrighty, so I'll write my integral. Now instead of 3x squared, I can write du dx, which takes care of this. I need the radical in there. That's part of it. So we'll put the radical in. All right, and then instead of putting x cubed plus 1 under the radical, I'll just put u. And that takes care of all this. And then I still need to write my dx. Okay, so my dx's cancel, yay, and I'm just left with root u du, which, as long as we remember that that's just u to the 1/2 du, that's really easy to integrate using reverse power rule. So we will bump the exponent up by 1 and then divide by 3/2, which is the same as multiplying by 2/3, plus c. Last step, back substitute for u. In this case, u is x cubed plus 1, so then all to the 3/2, plus c. And that's good. Just leave it like that. Okay. All right. So last example on this page, I am going to say pause the video. All right, and see if you can do this one on your own. I'm going to work through it, and then once you're done and have an answer, right, hit play, and the answer should be there. I'm not going to step you through this one, though. All right, so hit pause. Okay, welcome back, time travelers. All right, hopefully you got the answer in black at the bottom. At the end of the day, you can always check by just differentiating and make sure that you get back to the original expression in the integrand, right? So you can know if you're right. All right, so if you feel good with those three, I'd say we're ready to move on to the next page where we start to talk a little bit about more of those like edge cases and nitty gritty. I shouldn't say edge cases because it's what's going to happen most of the time. But basically what's going to happen when things don't work out perfectly, which again, that's the real world. Alrighty, next page. Okay, all right, so we're going to start and we're going to try to do things pretty much the way that we've done them, all right? So we're going to think to ourselves, all right, do I see a function and its derivative? And the answer is yeah, kind of, right? I mean, I see an x squared here, and I see sort of its derivative out here, right? The problem is that the derivative of x squared isn't x, it's 2x. But if you haven't quite figured it out yet, when we're doing calculus, a scalar multiple, like a 2x versus an x, is not a big deal. All right, so really the question we want to ask is, do we see a function and something that is at least of the right degree to be its derivative? And so here the answer is yes. And so we're just going to proceed as normal, and you're going to see how it's all going to kind of work itself out and fall in your lap. All right, so here, all right, we'll say that u equals, not just x squared, but how about x squared plus 1 to make our lives easy? Always lump in a constant if you can. All right, so now from here, when we get du dx, we're going to get 2x. Notice how I took du dx from u as I wrote it down, right? I wasn't thinking, well, oh, I only see an x, so I'm just going to write x. No, the derivative of u, as we defined it right here, is 2x. So that is what you write. Okay, so let's start now rewriting our integral and see how this all shakes out. I also apologize for the atrocious handwriting. I need that fancy iPad Pro with the stylus. All right, so we have our integral. Okay. I don't have anything that's exactly equal to x yet, so we'll come back to that. Ooh, I do have something that's equal to x squared plus 1, right? So I can, instead of writing x squared plus 1 to the 5th, I can write u to the 5th. All right, and that takes care of all of this. All right. Now, all right, I'll write the dx in. That's just going to kind of be there. Great. I need something that's exactly equal to x. I don't have that at the moment, but it won't be hard to get, especially if I just do a little bit of algebra right here, right? If du dx is equal to 2x, if I just divide both sides by 2, I can figure out that x is exactly equal to 1/2 du dx, right? And so that's something that is exactly equal to x that I can substitute in for x. So let's do that. Instead of writing x, I will write 1/2 times du dx. And then that's going to take care of x. And everybody in my integral is accounted for. Let's clean this up. All right, the dx's, they cancel. And so then I just have a 1/2 u to the 5th du. And the 1/2, that's just going to come out as a scalar multiple. That's not a big deal. All right, so then let's integrate u to the 5th. Oh, okay, the antiderivative is u to the 6th over 6 plus c. All right, and so then we'll clean that up and back substitute. So really we'll be looking at a 1/12 times, let's see, u is x squared plus 1 to the 6th plus c. Done. Great. All right, moving on to example 5. And guess what? There's an error in example 5 as well. Actually, we can integrate this the way that it is. This has its own antiderivative. That's really not too bad. But we're just not there yet. That's actually for section 5.8. So for now, I would like you to just pop an extra x in the numerator there. Okay, so it'll be x dx over 1 plus 9x squared. All right, so do we see some function and something that at least looks like it could be its derivative nearby? Well, sure, right? This 9x squared, right? The derivative of anything to the second is going to be something to the first, which would be this x that I so strategically placed right there. All right, so let's go with that definition of u. All right, so let's do u equals, and you know what, let's not just do 9x squared, let's do 9x squared plus 1 because, you know, let's just lump the constant in if we can. All right, and now, based on this definition of u, let's calculate du dx. So in this case, du dx, the derivative of expression u with respect to x is 18x. Great. All right, so let's start to rewrite. So here's my integral. All right, and then my whole denominator, actually, I can replace with u, right? That takes care of that. Looks like in the numerator, I need a dx. Great. And then I also need something that is exactly equivalent to x. I don't have that explicitly stated, but with a little bit of algebra right here, right, if I just divide both sides by 18, right, I will get something that's exactly equal to x, right? I will get x equals, right, and you could even say just du over 18 dx. Great, and so that's what I will pop in here for x, du over 18 dx. Fantastic. Everybody's accounted for. The dx's cancel. All right, and then let's start to rewrite. So really, this is actually a 1 over 18 du over u. Okay, well, the 1 over 18, that can come out. And really what we're actually looking at in here is a 1 over u du. It's kind of like, oh, whose derivative is 1 over u, or 1 over x? Well, that would be the natural log of x. So this is going to integrate to the natural log of u. And I don't think we've really discussed that before, but you should put the antiderivative, right, when you're using natural log, put the natural log of, use absolute value brackets, because we can't take the natural log of negative things. So throw it in absolute value brackets to cover all your bases. All right, so now when we back substitute, we'll get the natural log of 9x squared plus 1, which, okay, it looks like we didn't even have to worry about the absolute value brackets because 9x squared plus 1 is positive for all values of x. But hey, we did our due diligence. So you could drop the brackets and just use parentheses, or you could just leave it. It's fine. All right, great. Example 6 maybe gets a little bit more complicated, but hey, you know, we're smart cookies, so stick with me. Alrighty, so do we see a function derivative pattern? And I'm like, yeah, hey, I have something to the 4th and something to the 3rd. So obviously that something to the 4th can be my function, and the something to the 3rd can be my derivative. All right, so, all right, I'm going to call u, in this case, x to the 4th. And sure, let's throw in the -1. Always lump in a constant when you can. So now the derivative of that expression for u with respect to x is 4x cubed. So let's start to rewrite. There's my integral. All right, I need something that's exactly equal to x cubed. Don't have it. We'll come back to it. All right, then I have 3 to the x to the 4th minus 1. Oh, that's just 3 to the u. Thank you. Then we have dx. Okay, you're in there. And then let's figure out what is exactly equal to x cubed. Well, with the powers of algebra, we can figure out that x cubed is exactly equal to du over 4 dx. So let's write that. Du over 4 dx. Great. Okay, and now let's clean it up. So now we will have, well, the dx is canceling. We'll have a 1/4 on the outside, right, because it's all over 4. And then the integral of 3 to the u du. And we're like, oh, hey, I have an exponential, right? That's not base e. It's an exponential in base 3. So you're going to learn a rule for integrating an exponential in any base. But for now, let's actually do this using another u sub. All right, so let's just call 3 to the u our function. All right, and I'm going to do this in a different color so that you can see. And I don't want to use another u because that's going to get confusing. Let's use y. Okay, so let's let y equal 3 to the u. All right, and now let's go get dy du. So what's the derivative of 3 to the u with respect to u? Well, if you remember, the derivative of any exponential is itself times the natural log of your base. Fantastic. All right, so we're going to now continue rewriting this using this like second level u sub, which is actually a y sub here. All right, so let's rewrite. I have my integral. All right, I'll put my 1/4 out here. Almost forgot about you. Okay, and now 3 to the u, I am calling that y, right? Okay. And then I need something that is exactly equivalent to du. Okay, that's going to take like a little bit more algebra, but I think you can do it. All right, let's come down here. Let's cross multiply. All right, so we'll get dy equals 3 to the u ln 3 du. Therefore, du is exactly equal to dy over 3 to the u ln 3. All right, so let's write that in for du. All right, du is dy times 3 to the u ln 3. Oh no, we've got u's and y's, and I'm just not, I mean, this is single variable calculus right now. This isn't multivariate calculus, right? I just want one variable to integrate, please. But oh, remember this 3 to the u down here? That's just y. So let's write it like that. We'll have 1/4 integral y dy over y times ln 3. Okay, and then these y's cancel. And you will be left with 1/4, and then the over ln 3, that's just a constant. So let's bring it out here, times the integral of dy. And that is really easy to do. All right, this is going to take up a little bit more room, so I'm going to scoot over here. So that's going to be 1/4 ln 3. And then the antiderivative of dy is y plus c. All right, so then let's back substitute for y, 1 over 4 ln 3. What is y? Well, that's 3 to the u plus c. That's a plus sign. And then let's back substitute for u. What is u? Wait, what is u? Let's come over here and look. U is x to the 4th minus 1. Okay, so that's going to be 3 x to the 4th minus 1 all plus c. Okay, which, you know, if you wanted to make this a little bit more compact, you could say 3 to the x to the 4th minus 1 all over 4 ln 3 plus c. And that's your final answer. All right, but from here, you would be able to figure out the shortcut for integrating an exponential in any base. All right, so let's just come down here into the corner. All right, and this is going to be something that you want to put on your integration rules sheet. I think it's your gold sheet, right? The antiderivative of a to the x with respect to x will be, well, the antiderivative of any exponential is itself, but now we'll just divide by the natural log of the base plus c. And we kind of saw that, let's see, where did we see that in here? Right over here, okay? Right, itself over the natural log of the base. All right, so, I mean, you can do a u sub every time, but that takes time. Okay, we're almost there. All right, the last page talks about what you should do when you don't see any function / derivative pattern at all. Guess what? We can still do something. So let's go. Okay, so notice in example 7, I don't see anything that looks like, oh, this could be the function and this could be its derivative, right? I see an x and an x. And that's not even of the right order for one to be the derivative of the other. All right, but basically we're just going to kind of proceed like we normally would and kind of hope that it works out. And sometimes a nice thing to do is to just ask yourself sort of what's the more complicated or complicating part of the problem, right? And that can help you choose u. Right now, the complicating part of this problem, I would say, is the radical. That's the thing that's going to make this difficult to just integrate by simple methods. So let's just call everything under the radical u. So u will equal 2 minus x. And now, what is du dx, right? And here's where it is really important that you're pulling du dx from here, not from the original problem. All right, because notice, du dx is just a -1. All right, and we don't really see that anywhere here. All right, but do not let that deter you. Okay, so notice, we may not really know where this is going yet. That's okay. All right, this isn't one of those things where you need to have a perfect plan before you even get started. Sometimes the math kind of does itself for you as long as you're, you know, going about it correctly. Okay, so let's just start to rewrite. Let's see what we need. Okay, so let's get our integral in there. Okay, and then the x plus 1, I don't know. All right, I don't know about that. We're going to come back to it. All right, but for now, I can replace root 2 minus x and instead write just root u. Okay, cool. All right, dx. What is dx equal to in terms of u? Oh, all right, well, for that, I can come down here, right, and with a little bit of algebra, right, I can, if I cross multiply, right, I will get that negative dx equals du, therefore dx equals negative du. So that's a way that I can replace dx with something in terms of u. All right, so instead of writing dx, I'm going to write negative du. All right, now, x plus 1. All right, I don't have anything that's exactly equal to x plus 1. And I'm not really going to worry about the plus 1. Again, constants, they're not usually so much of an issue, all right? Instead, let's focus on finding something that is exactly equal to x, all right? Remember, we want to change things from using x's to using u's, all right? And, oh, where did I establish the relationship between u and x? Why, right here. So actually, I'm going to just bring this down here, right? And if u equals 2 minus x, I can use algebra, right? And then say that u plus x is 2. Therefore, x is equal to exactly 2 minus u. So that's what I can write instead of writing x. So let's write 2 minus u. Oh, and then we still need to get the plus 1 in there, right? So that everybody's accounted for. Okay. Let's clean up this integral. Okay, so let's see. This bit right here is going to simplify to a 3 minus u. And then, all right, that takes care of this guy. Then we still have a root u. And then we have a negative du. I'm just going to put the negative out front, right? And then write the du in here. So we're good. Our integral is all in terms of u's. Fantastic. All right, how do I integrate this? This is still a product, right? That's okay though, right? This is not a product that we can't deal with, right? We can just distribute. So let's say negative, and then we'll do 3 times root u. I'm going to say 3u to the 1/2, and then minus, okay, u to the 1 times u to the 1/2. That's u to the 3/2. And then all of this integrated with respect to u. Okay, so let's get the antiderivative. We've got a negative out front here. And then we'll have 3. And then u to the 3/2 over 3/2, which is times 2/3, minus u to the 5/2 over 5/2, which is times 2/5. All right, and then plus c. So we'll simplify and back substitute, and we'll get, right, these guys will cancel. We'll get negative 2. U is what? 2 minus x to the 3/2 minus, well, actually plus when we distribute this negative out in front. So plus 2/5 u again, 2 minus x, to the 5/2 plus c. All right, not too bad. All right, so big takeaway from this is that sometimes you just need to solve for x completely in terms of u in order to find an acceptable replacement. All right, so let's try that last but not least with number 8. Whoops, I guess there is a number 9 as well though. All right, no big deal. Okay, so, all right, for example 8, do I see a function and its derivative? Not really, right? 2x, its derivative would just be 2, which is not the same order as x, but we're going to go ahead as we think we should go anyway, all right? Typically, if there's a radical involved, you can just throw whatever's under the radical and call that u, all right? Usually, like, your grouping is going to be, you know, sort of a good indicator for how you should choose u. All right, so let's do it. U equals 2x minus 1. And so then, in this case, the derivative of that function u with respect to x is 2. And that's kind of all we need for right now. All right, let's start to rewrite. Okay, well, I know that at least in my denominator, I can put root u, right? Let's see. Something that is equivalent to x. All right, well, let's use this definition here and solve for x. If we solve for x in terms of u, we will get, what's that going to be? U minus 1 over 2 will be exactly equal to x. All right, so actually what I'm going to do is I'm just going to put a 1 up here, and I'll do a u minus 1 over 2 right here. Great. That takes care of x. And then I need something that's equivalent to dx. but uses u's, so that will come from here, right? If I use algebra here, I can figure out that dx, let's see, when I cross multiply, I get 2 dx equals du. Therefore, dx is exactly equal to du over 2. Great. So for dx, I can instead write du over 2. Yay, everybody's there. All right, let's clean it up. Let's see, I'm going to pull out this stuff from the denominator. I'll pull that out as a 1/4 in front, and then I'll have u minus 1 over root u du. And again, we start to get a little bit nervous because we're like, integrating this, how is this better? But it totally is better, because why? Because it's an STD, and we love STDs. All right? Hopefully there are no parents within earshot. Alrighty, so I can basically just split this up as, all right, so u over root u is, well, u to the 1/2, and then minus, that would be u to the negative 1/2 du. And now it's easy peasy. Okay, so the antiderivative of u to the 1/2 will be u to the 3/2 over 3/2, which is times 2/3. All right, and then the antiderivative of u to the negative 1/2 will be u to the positive 1/2 over 1/2, which is times 2 over 1, plus c. All right, so let's back substitute. So you'll have 1/4 times 2/3, and then in this case, u is 2x minus 1 to the 3/2 minus 2, and then 2x minus 1 to the 1/2, or, I mean, you could just say root 2x minus 1 plus c. You could distribute that 1/4 in. It's probably a good idea. Ooh, this should be 3 over 2 there. All right, but I'm just really trying to get at the idea here. Okay. All right. Now number 9. Number 9's a little bit tricky. And it's not tricky because of the calculus. It's tricky because you need to remember some of your exponent rules. All right, but let's take a stab at it, because really we don't need much at all to do this one. All right, I just wanted to sort of show you, you know, what happens and how we can kind of play around until the math helps us in a way. And so I'll get the question a lot, like, oh, how would I know to do that? You don't. You try it. All right, so I'm just going to start, I think, because I can, honestly, I'm just going to start messing around with the expression in the integral, right? I've got root e to the 3t minus 2. Well, I am going to use some exponent rules. I am first going to use the fact that if I have, right, x to the n over x to the m, that's really x to the n minus m, all right? And say, oh, so really here, that just means I have e to the 3t over e squared, right? That's all under the radical, right? I subtracted their exponents, therefore they must have been divided first. Then I'm going to use a property of radicals that says the square root of a over b is equal to the square root of a over the square root of b, right? So that I can write this as root e to the 3t over root e squared. Oh, hey, so that's something, right? What's the square root of e squared? That would leave us with root e to the 3t up top and just an e on bottom. So I am now going to start rewriting this integral. All right, I have, an integral, and I have the square root of e to the 3t all over e dt. All right, And now here's the thing, remember, e is just a number. That's a constant, so I can actually write this as 1 over e on the outside and then write my integral, right? E to the 3t dt. Furthermore, I will also remember that raising something, or I'm sorry, taking the square root of something is the same thing as raising it to the 1/2, right? So I'll have 1 over e times the integral of e to the 3t all to the 1/2. And then when I am raising a power to a power, I am just going to multiply their exponents, right? So I'll have 1 over e times the integral of e to the 3/2 t dt. Okay, so now might be a good time for a u sub, like, right, because I can integrate e to the x. That's easy. Integrating e to the 3/2 x, you know, I don't know. All right, so let's call u 3/2 t. All right, and then in this case, du dt would just be 3/2. Great. All right, so let's start to rewrite our integral. We'll have 1 over e, just a scalar multiple, the integral sign. Then we'll have e to the u, that takes care of the e, that takes care of the 3/2 t, and then dt. Okay, we need something that is equal to dt. Again, we can get that using algebra here. If we cross multiply, 2 du equals 3 dt, therefore dt must be exactly equal to 2/3 du. So let's write that in, 2/3 du. We'll pull that 2/3 out in front, so we'll say 2 over 3e times the integral of e to the u du, and then it doesn't get simpler than that, right? You'll have 2 over 3e. The antiderivative of e to the u is e to the u plus c, and then we back substitute. So we get 2 over 3e. U in this case was what? Oh my gosh, I lost it. 3/2 t. So 3/2 t plus c. All right, and you could actually technically take it a step further. I'll show you over here. Right, you could say that this is 2/3 times e to the 3/2 t over e. And then, oh hey, dividing like bases, let's just subtract their exponents. So you would ultimately get 2/3 e to the 3/2 t minus 1, and then we can't forget our plus c. And, you know, at the end of the day, you could just check it using differentiation and make sure that it all works out. But I think that's enough for today. All right, your next step will be to do the suggested exercises and email me with any questions that you might have. Happy U-subbing!